One of the greatest and yet one of the simplest lecture demonstrations that I know of was first performed 180 years ago at this bench by Humphrey Davy. With Bryson's help, I'd like to repeat this. Through this wire runs a current of electricity. If we just increase the applied voltage, you can just see as we continue to increase that that wire glows red. Now we drop the voltage so that it is no longer visibly red. There is still, of course, a current passing through it. Down it goes till it's virtually invisible. Humphrey Davy just took a lump of ice and stroked that vigorously like this. And now if you look at the other end, see what happens. As I stroke it with ice-cold material, thank you, Bryson, that gets red hot. Now, there's a very easy explanation for that. It's because when we drop the temperature of a crystalline material, a crystalline metal, its resistance decreases. Not all materials behave like that. Certainly a lump of copper, as we have here, would, and the resistance of this is very low indeed. Watch what happens on the meter. It's a very good conductor. Graphite, our mineral friend from last lecture, also a pretty good conductor. But silicon, no, that's not quite so good. We can barely see any current passing. Quartz, however, is an atrociously bad conductor. They all contain electrons, but the electrons are not free in that quartz. Now, I want to emphasize this point because it's a very remarkable fact, and I want some help. I'm going to walk up these steps, and I'm going to ask for some assistance. When I pull this out, I want to give you this. What's your name?
Krishna.
Krishna. Now, Krishna, I want you to hold that end. And what about you? Who can help me here? What about you in yellow? What's your name?
Matthew.
Come along, Matthew. Now, get hold of this. And don't pull it until I tell you to, and don't pull it too vigorously, will you? It's very fragile. You hold it steady, Krishna. Now, wait for me to get back, and then I'll ask you to unfurl that, and I'll then be able to comment on what is to be seen. Right, Matthew, you can go quite slowly now. Here's fused quartz. Very high resistance indeed. Sulfur, only marginally less. Diamond, also pretty high resistance. All these are insulators. Ceramics, in other words. Now comes cadmium sulfide. Most glasses. Silver bromide, our friend from the first lecture, which is used in every photographic film. Then comes silicon, another important semiconductor. And shortly we shall see germanium, another important semiconductor. And then entering slowly into the field of metals comes bismuth, iron, and copper. If I were to cool copper, as I just did with ice, its temperature would drop even more. It would drop by perhaps 100-fold. Now you can put that down now. Just put that down. Thank you very much. Now this business of dropping the resistance when you drop the temperature, there was a man named Onnes in Leiden University who in 1911 was studying mercury, quicksilver. Now Bryson is going to prepare crystalline mixed silver, quicksilver, and I have the liquid quicksilver, mercury there. What Honors did in 1911 was to measure the resistance as the temperature continued to drop. And as you would have expected on the basis of the experiments of Humphrey Davy, the resistance gradually dropped and dropped and dropped. Now, once we get to the crystalline state, which I hope we shall get to very shortly, let's see whether this has become a crystal. You see, it's like taking melted TNT and forming crystalline TNT, which is what we did in the first lecture. Here we have melted, because at room temperature, quicksilver is molten. If we cool that, down it comes to crystalline, solid mercury. There it is. It's now a lump of solid crystal. Kamerlingh Onnes observed this incredible fact. It really was incredible. The resistance decreased, but suddenly it plummeted down and became zero. Now, I really mean zero. You remember where Krishna was standing? He represented copper at room temperature. Do you know where he would have to stand if we talked about the resistance of crystalline mercury at the absolute zero of temperature, minus 273 degrees centigrade? He would have to go way, way to my right, not just as far as Buckingham Palace, not just as far as the Antarctica, not even to the sun. He would have to go to the edge of the universe. That's how much it dropped. Now, that was so tremendously shattering for Kamerlingh Onnes. He took 2 years before he published the results of what he had discovered. He repeated it on numerous occasions. It was true right enough. There was no question about it. Well, 75 years or so elapsed, and there was comparatively little excitement. People certainly began to know, they understood why metals became superconducting. That was done about 25 years ago. 18 months ago, in Switzerland, 2 gentlemen working in the IBM laboratories reported something very dramatic. A material, an oxide, which was superconducting at about 40 degrees Kelvin, 40 degrees above absolute zero. But just about this time last year, when we were enjoying the Christmas lectures, a report appeared, and I think it's the first newspaper to report it. It wasn't any European newspaper. It was the People's Daily in Beijing. Here it is. It's marked the 27th of December, 1986. And on the front page here is a very dramatic announcement, which says that scientists working in Alabama, in Texas, in Tokyo, and in Beijing, simultaneously and quite independently, using a material which you could form from copper, like this copper that comes from Cornwall, but you oxidize it and form copper oxide. You take barium carbonate, like this lump of mineral witherite, which comes from County Durham. You mix them together and you put some more oxide in, yttrium oxide, of which there is plenty in China and in India. You stir them up, you form a molten mass, you let it cool, and you have a crystalline solid which is superconducting at above liquid nitrogen temperature. Now, that was a phenomenally interesting fact. Let me just emphasize. My 2 Chinese students working with me in Cambridge took this electron micrograph about 6 months ago. Now, as I told you in the last lecture, color ceases to have meaning under the electron microscope. You can either have contrast of black or white. This black or white is the sort of projection of the atoms in this material. And in fact, if we look more carefully at this colored region, the yellow parts represent yttrium atoms, the red part represent copper atoms, the blue part represent barium atoms. And that's yttrium 1, barium 2, copper 3, and oxygen. And just to emphasize that point further, my colleague Dr. Andreas Novak has placed up on the graphicon screen the further representation of the structure of this important superconductor, with the yttrium in yellow the barium in blue, and the copper oxide regions in red, so that the 1, 2, 3 type structure is apparent from that, the new superconductor. Now, this effect is so dramatic, I have invited a friend, Dr. Colin Goff of the University of Birmingham. Dr. Goff. Dr. Goff comes from a team of material scientists in the University of Birmingham, and they've been working on superconductivity. Colin, the first thing our friends would like to see, I'm sure, is the real proof that there is such a thing as zero resistance. Would you help us there?
Certainly. What we have here is a rod of the newly discovered superconducting material. You can see that it's black, unlike most other metals. In fact, it rather looks like the lead on a lead pencil. The properties of the superconductor, in some ways, are rather similar to those of the lead pencil, where conduction comes from electrons travelling along the layers of carbon in the graphite structure. But in the newly discovered superconductors, the conduction is believed to come from the electrons jumping in layers of copper atoms, and the electrons jump from copper atom to copper atom using oxygen atoms as stepping stones. But what we have here is a measurement of the resistance, and you can see that this meter is recording the resistance of the little rod of material, and at the moment it's at room temperature, and it's acting just like a normal metal. But what I'm going to do is to lower it into liquid nitrogen, which is therefore going to cool it, and cool it below the transition temperature. You can see that the resistance, first of all, coming down rather slowly and then suddenly dropping to zero. What we have here is absolutely zero resistance. This is a superconductor.
Colin, we'd like you to move on and demonstrate this phenomenon of levitation.
Well, the properties of superconductor, in terms of their magnetic properties, are even more interesting than the fact that they lose their resistance. We're all familiar with the fact that a ferromagnetic material, like iron, is attracted to a magnet. And the superconductor has just the opposite properties. If we bring a superconductor up to a magnet, it will in fact be repelled. And conversely, if we bring a magnet up to a superconductor, it will be repelled. And we can show this in this little demonstration. What we have here is a lump of the superconductor, and it's being cooled at the moment in this chalice containing liquid nitrogen. So it's quite cold. It's not yet quite cold enough to become superconducting. So I can put it on top, and you can see that this magnet is just sitting on top of that block of material. Now, if I cool it a little more by putting some more nitrogen on the top, and you watch that magnet, watch it very carefully as I pour the nitrogen on, and I've got to wait for it. Now, did you see that? It's lifted right off. It's levitated itself. Can you see the gap just underneath there? If I now pick it up, just to convince you, I put it back on top, and you can see it floating in space. I can turn it round, I can spin it, turn it towards the camera, I can just spin it round that way a little. You'll see it spinning even more. That is magnetic levitation. And of course, that's an exciting thing. We've never been able to demonstrate it so easily as this in a laboratory lecture like this.
Colin, there's yet another manifestation of that, isn't there? Go on to the paddle wheel experiment, which was one of my favorites.
Well, we have here an experiment in which we can have the equivalent of frictionless bearings. In this experiment, we have two cups made out of a superconductor. This is the same material, superconducting yttrium, barium, copper oxide, made in little cups which would support a magnet if we put it in there. And I have here a little rotor. We have a look at this little rotor. It's very light, and it has a very strong magnet on either end, so that if I drop it onto the magnetic cups, it should float in space. There we are. You can see it rotating around, floating in space. And then if I give it a little jet of air, we can cause it to turn round. I can get some air by boiling off a little bit of liquid nitrogen here. And the liquid nitrogen comes off, and there we are. We have a rotor spinning very fast with frictionless bearings.
Thank you. Now, Colin, this could have repercussions in transport, for the future at any rate. Perhaps one could illustrate this But after I remind our friends that in Japan already there is a monorail system which works on the principle of superconductivity. In this train there is a magnet which is cooled to liquid helium temperatures, a very expensive thing to do. And there's a monorail system there, so consequently, using that principle of levitation, one can attain speeds with this vehicle of 550 kilometers an hour. How about illustrating what might be possible in the future?
Well, of course, the scale is a little bit different. We can't get our train into this lecture theatre. And what we have here is a rather small-scale version where we are going to support, unlike this experiment here where we supported a magnet on top of a superconductor, here we're going to support the superconductor on top of a magnet. And the magnet is your railroad of the future. We have two strips along here of magnetic material. And I'm going to put onto it a tiny rod of superconducting material, which of course I've had to cool to liquid nitrogen temperatures. But once it's cooled to liquid nitrogen temperatures, it will float on our magnetic track, and you will see it going backwards and forwards. It's our little commuter train of the future.
That's right. But when it warms up, it ceases to be a superconductor, and then it doesn't any longer act as a train. Thank you very much indeed,
Thank you.
Colin. Now, there are two things in addition that I want to say about superconductors. Number one, quite apart from these engineering aspects, the transport of the future, there are many other repercussions that are possible as a consequence of discovering superconductivity at high temperature. You can design instruments with known physical principles which are capable of picking up the magnetism that's in our body. You know, when electric currents pass us, they do all the time in our bloodstream because there are charged atoms there, they generate small magnetic fields. Those magnetic fields are therefore detectable if you have a good enough superconducting instrument. And that's precisely why I put this drawing here. The neuromagnetism associated with every human or living brain has a characteristic pattern. And for the normal person, there'll be a characteristic normal pattern. For a person suffering from a brain hemorrhage or about to suffer from some brain illness, or for example an epileptic fit, one might be able to monitor it in advance with the kind of technology that's now being discovered. I should mention, at the moment there are reports of having materials, new materials made, which are superconducting not at 90 degrees Kelvin, 90 degrees above absolute zero, but something like 150. The goal is to get it at room temperature. Then the world becomes vastly different. As Dr. Goff said, we can dispense possibly with the wheel that has been with us from the beginning of man almost. That's the sort of thing. But let me emphasize, as yet there is no direct evidence that a material does exist which has superconducting properties at room temperature. But absence of evidence is not evidence of absence. Now, I want to go on to deal with semiconductors. Dr. Goff mentioned diamagnetism. The man who coined that term was Michael Faraday. Michael Faraday was a very remarkable gentleman. Here's one of his notebooks. He was a very methodical gentleman also. He wrote down every experiment that he carried out. On this page, on the 21st of February, 1833, he shows a little drawing of a sort of U-tube, very, very small drawing in the corner here, a U-tube. And into that U-tube, just as Bryson has got here, he put silver sulfide. He describes on paragraph 318 that this sulfide, when hot, seems to me very much to resemble the metals in the usual state as to electrical relations. Now, what he meant by that was that the solid, on heating, became a very good conductor. What does that mean? Very opposite from what we saw earlier. As you cool copper, and mercury becomes a better conductor. when you heat this, as Bryson is now going to do, we shall see whether it becomes a better conductor or not, because in this circuit we have a little meter. Well, the meter is very simple. It's a little bulb. And if a current passes through this solid when Bryson heats it, then we ought to see evidence of that current by the bulb lighting up. True enough, it works. Thank you, Bryson. Now that's semiconductivity. You remember the chart that Matthew and Krishnan opened out for us? I had insulators and ceramics and metals, and in between I had semiconductors. Not only because they have intermediate magnitudes of resistance, but also we call them semiconductors because they increase their capacity to carry current with increasing temperature. Now, the material that Faraday handled in 1839 is very different from the popular semiconductor of the 20th century. Let me tell you that silicon especially, and germanium also, can be made, as no doubt you know, into transistors. What does that mean? I take a very pure slab of silicon and I put in 1 atom of boron or 1 atom of phosphorus, shall we say, per 10 million atoms of silicon. And I totally change the character of that material. That itself is dramatic. You know, it's like taking the population of China and putting 1 European there, and you change the entire practices of China. They no longer speak Chinese, they no longer understand Chinese music and so forth. They don't eat any more Chinese food. That's the kind of analogy that one may draw. Now, a transistor is simply 1 type of silicon with boron in it, 1 with phosphorus in it, and a junction formed, and it acts as a kind of valve. 20 years ago, if you had a circuit that had to do a certain electronic job, it would have been like this. There are 2, 4, 6, 8, 10, and 10, 20 transistors there. Now, you can't see the transistor, but in the intervening years, what has happened has been extraordinary. Here's now a single crystal of silicon, quite a wide diameter. We can make this of exceptional purity. 20 years ago, it was difficult to make it any larger than of that diameter. Then gradually it improved. Now you're beginning to see something. We've now got what is called the integrated circuit. As part of this wafer, this very thin wafer that you can cut thousands of them from a boule of that kind, and onto each you can put an integrated circuit. Here's an integrated circuit. We'll see it shortly inside the scanning electron microscope. Do you know how many transistors there are here? 21,000. Let me show, with the aid of Paul's help. Let's see the integrated circuit, Paul, on the scanning electron microscope. Here it is. Now, in one very minute corner up here, we have a few hundred transistors. Now, Paul, in a moment, is going to tell us a little bit more about this electronic brain. This integrated circuit, I should tell you, is capable of sustaining 256 simultaneous telephone conversations. That's what it was made for. Let's see this brain actually thinking, because this instrument that we have, when we switch on the current, as you should do now, did you notice the change in contrast? You see, the instrument is sensitive to regions of the circuit that carry current. Let's send a message through. Now you can actually see it thinking. Look at it. That is the brain in operation, the electronic brain, the micro-miniaturized brain of the modern and future world. There are many more developments of that kind to come. Micro-miniaturization has reached a stage now where it is very difficult to fathom how dramatic it is. Thank you, Paul. If I were to tell you that I have a Christmas card on my pin here, I've got a little pin in my lapel. Can you see that? Just that minute pin. I have friends in the University of Cambridge who have the ability to write messages so small that I could put 1 million Christmas cards on this particular pinhead size. Here's the Christmas card that he has sent, Dr. Berger and Dr. Nixon from Cambridge. They've sent us a Christmas card. Now, they know of my affiliations with King's College. You know, you could put 100 million of these King's College chapels into one postage stamp. The RI lectures, greetings from the Cavendish, Merry Christmas, and there it is also in Welsh, Nadolig Llawen. That's a greeting from Cambridge. Now that's semiconductors and integrated circuits. We can put semiconductors to other use. You can convert light into electricity. Again, it's a matter of putting two junctions together. Silicon with, shall we say, phosphorus in it, silicon with boron in it, and you form junctions. Now, Bryson is going to help me to lift this solar panel, which is made in Britain, and it is typical of the kind of panel that you would use to generate a couple of 100 watts of electricity. If we gently let it down again, you can see this is polycrystalline because of the glistening small particles in each plate. This is single crystal, and as we bring this up, you don't have such an effect. Now you can put several arrays of these, hundreds of them, depends how much power you want, and then you generate electricity locally if you have plenty of sunshine. Now that's a very important ability to have. Here's another mobile power source. If you're out in the desert, if you're camping, if you're in a hospital, if you want some special assistance with light, you let this be exposed to sunlight during the day, and then you carry your light along with you. 40 watts, and off you go. So you've got enough power. Now I'd like a volunteer, somebody rather small. How about you? What's your name? Sorry? Fergus. Good to meet you, Fergus. Now, I want you to stand about there, right? Now, face me, right. Fergus, I'm going to place this hat on your head. It's a special hat. I hope it'll fit you. I've got a solar cell there, and I'm going to put it on your head. All right? My goodness me. Now, you can't see me. I can assure you I'm doing nothing nasty, right? I've got an artificial sun here. I'm going to switch on some sunlight, right? Now, I'm going to bring it towards you, and we'll see what happens. See? Look now, as I bring more sun. See, you're being cooled down. See what's happened? You've got a little fan there that's helping you. See, let me do that again. So you could walk. That's tremendous, Fergus. You could walk through the desert, and you'd be kept cool with this little hat that's made in Hong Kong. Right? Thank you, Fergus. Good. Now, there are semiconductors which have even more remarkable properties. Germanium, for example, changes its conductivity, changes its resistance. It drops precipitously when light shines on it. But this material in here, cadmium mercury telluride in this tube, is really truly remarkable. You can make a new type of camera out of this, because it's so sensitive to radiation, the radiation coming from your body and from my body, the infrared heat that I'm liberating and we're all liberating at any time. That is enough when it strikes that cadmium mercury telluride to change its resistance so dramatically you can use it for a very special type of camera. If this room were plunged into darkness, suppose this were plunged into darkness, as it now is. Now, I can no longer see you, but if that camera that I talked about is working properly, then you ought to be able to see me. Excuse me. Now, also, as I put my spectacles on, you should see whether I have I'm wearing spectacles or not. Now, not only can I be seen by you, I can also be seen by Mr. David Smith of the Royal Signals and Radar Establishment at Malvern. He has a mobile camera, and at this moment he's walking into the lecture theatre. I can hear his footsteps, and I can sense his presence. Sorry, thank you. Good to see you, David. Good to feel your presence. Now, this camera of yours, tell us a little bit more about that, and the one that's being operated by your friend Martin Thomas up there.
Yes.
Tell us a little bit more about it.
Well, the principle is very simple. We're all very familiar with very hot objects, such as the sun or an electric fire radiating energy. Well, cooler objects radiate too. It's just that the cooler they are, the less energy they radiate, and the longer the wavelength of that radiation. So we're all radiating, as you said. If we want to detect that radiation, we have to build very special detectors made out of the material you've got there, cadmium mercury telluride. And because we're looking at the heat emitted by us all, that is easy to detect with the camera, and it doesn't require any illumination.
David, this gives us a wonderful opportunity to redo an experiment that was first done by the founder of the Royal Institution, Count Rumford. Count Rumford was puzzled by the fact that when he was being entertained royally in London, he was an American gentleman, incidentally, named Benjamin Thompson originally. He came to London. He was lavishly entertained in various places, as you know. He was a little bit distressed by the fact, as a scientist, that when he was served coffee, the coffee was more often than not in the aristocratic homes served from a gilded coffee pot rather than from an ordinary porcelain pot. He thought this was pure aristocratic affectation because he knew as a scientist gold conducts heat better than porcelain does. If you put hot coffee, let's put some hot water, make it do ersatz coffee, shall we say, right? Good, fine, that's my cup of coffee, and let's have yours. About the same amount. Incidentally, these have been made specially for the RI for this occasion by our friends in Worcester. Now, we've got hot coffee in there. The ladies who entertained him said, now look, it's much better to have a coffee pot made of gold or gilded rather than one like this. And Rumford said otherwise. Now, which was right, do you think? Do you have an idea? Anybody know? What would you say? Okay, well, let's actually see. Let's actually see. This, if I can point to it, let's view this and view that on the thermal imaging screen. You can see this one is certainly losing its heat more rapidly because you can observe it on the monitor, whereas that is not. Very nice example. But you can tell us many other examples, David.
Yes.
Why don't you go ahead and
Right.
use...
I'd like to show you a little bit of videotape now. A little earlier this year, I went to the Severn Valley Railway in Worcestershire and took the thermal camera and a television camera. This is the TV camera, ordinary black and white, nothing very remarkable. You would expect the engine to be hot. You will see when I switch now to the thermal imaging camera, white is hot, very hot engine, but you can also see the carriage and the vegetation in the background. This is an aircraft at Birmingham Airport, and you can see just the navigation lights and landing lights and a few lights in the background with the black and white TV. But again, when I switch to the thermal camera, as we do here, you can see the aircraft perfectly well at night. Black is hot in this case, black wheels and a black engine. This shot is a split screen. The top half is a television picture and the bottom half a thermal one. And we have some soldiers walking through a smoke screen. Now the thermal radiation penetrates through the smoke screen very easily because it is a much longer wavelength than the visible radiation, about 20 times, and it's not scattered so easily by the smoke. If you watch this soldier, you'll see him appear in a moment in the visible waveband.
David, come along and go to the other side of this black polyethylene screen. I'm sure you can tell us some interesting things about this also.
Well, in just the same way that the longer wavelength of the infrared radiation was able to pass through the smoke, so it is not absorbed by this black polyethylene screen, which obviously absorbs the visible radiation. If we look now in the infrared region of the spectrum, you should be able to see Professor Thomas standing the other side of the screen. Perfectly transparent. not only is that behaving differently, but so too is this. I have here a piece of ordinary window glass, which obviously we can all see through in the visible region of the spectrum. But again, if we now look in the infrared region, you'll see that it's very absorbing. And so the infrared is not quite the same as the visible radiation.
David, you asked me to provide you with a telephone directory. Why did you want that?
Well, John, I wanted to give you some idea of the infrared sensitivity of our camera. It is a very sensitive camera, and obviously we have some fairly sophisticated techniques for measuring sensitivity. But one simple technique that I like, which I think will illustrate to you all just how sensitive it is to leave my handprint on the front cover of this telephone directory. If we go to thermal band now, you can see the handprint left behind. But not only is it left behind on the outside, you can see it on the inside. And not only on the inside of the first page, but if I leaf through the telephone directory, that's about 40 pages. And here we are, 70 pages, and possibly you can even, no, it's not quite visible, but it goes to about 100 pages if we turn the gain up on the instrument.
Well, thank you very much indeed, David.
Thank you.
Very much appreciated. Now, we talked earlier about converting light into electricity. We can do the reverse with the aid of semiconductors. Let me tell you how that happens. If you have a special type of semiconductor in which there's an energy level there, shall we say, and another energy level there, and you'll remember what Professor Phillips told us in the first lecture, depending on the separation of energy, if an electron drops from one level to the other, then light of a certain characteristic wavelength is liberated. All we do, and this was an idea that first cropped up in Russia about 25 years ago, is to have a battery. One feeds electrons into the semiconductor, builds up a surplus at this level, one takes away electrons from here, deprives that of electrons, and consequently there's a tendency for electrons to drop down. If this separation is right, we get light emitted. And that's the LED, the light-emitting diode that you've heard of. Here's a good modern example. It's going to be the traffic lights of the future. If you look there, you will see go, wait, it was going so quickly that I can't even read it. Stop, wait, and go. And stop, wait, and go, and all sorts of cartoon characters. Thank you, Bryson. Now, why would you say is it so necessary to replace ordinary light? We've got good traffic lights after all. Why don't we bother to go this far? If I tell you that ordinary electric light is terribly inefficient, if I could ask you now, there's a certain amount of electricity that goes into an electric light bulb. As a percentage of the energy that goes in, how much light do you think comes out? Can I have a show of hands? Say, how many would believe that it's more than 80%? Well, there are lots of skeptics around. More than 50%. Okay, we're beginning to get some action. More than 40%. 30%. 20%, 10%. Well, you're all wrong. It's just less than 5%. Only a 20th of the energy that goes in comes out. I have in my hand, made in Tohoku University in Sendai in Japan, a gallium arsenide torch in which there's 30% of the energy going in coming out as light. That's the incentive to go to light-emitting diodes. That's one of the incentives. There are many other incentives. Let me tell you, with the help of Mr. Peter Williams, who's in the wings here from the Alan Clark Research Center.
Yeah.
Thank you for coming along, Peter. Peter brought with him from Northamptonshire a very, very small laser chip. It's indium phosphide gallium arsenide. Do you remember that gateau cake that I showed you in the first lecture? That's what it's built up as. But this dimension, you must remind me, Peter, is only 1/3 of a millimeter.
That's correct, yes. Yes.
1/3 of a millimeter in width. And the laser part, which we're going to see shortly, is the size of a pinhead in there.
Well, it's about 1/1000th of a millimeter.
1/1000th of a millimeter. He's got it under this microscope, and I might tell you that this is being seen under ordinary illumination at the moment, but he's got a germanium crystal detector in here. And what Peter's going to do shortly is turn on the voltage, and suddenly the current will break through. And when that happens, go on, Peter, we're getting laser light emitted. That's the laser bursting of a star, as it were. Well, is it really? The fact is that that's invisible. You see, the light that I've got here is red light. The light that Peter has switched on is infrared light. It's twice the wavelength of this red light, and it comes about there. Now, there's a remarkable fact about that, Peter, isn't there? That's the kind of laser that one has in these fiber optics these days.
Certainly, yes, yes.
You also use it in medicine. In the 6th lecture, Professor Phillips and I will be describing the endoscope and so forth. But remind me, Peter, there's a tremendous amount of information you can pack into messages, into fiber optics. What's the sort of information rate?
Well, there certainly is. Although we're running this device in a fairly continuous way, this particular laser on here is designed to operate at over 2 gigabits per second, which means that the light can flash on and off at over 2,000 million times a second. And that's an awful lot of information.
2,000 million times a second. Do you know what that really means? How many telephone conversations?
Well, it's the equivalent of tens of thousands of telephone conversations.
Per second.
Simultaneously.
Thank you, Peter. Now, that's taking us through to the final part of my lecture. I'm going to talk about the influence of light again on a semiconductor, but this time, and I need a volunteer, where can I have, what about you? You come along. What's your name? Helen. Now then, Helen, I want you to do a simple but important job. I want you to stand here, and I want you to look very carefully at that as soon as Bryson switches on the light. You look at it. I'm going to tell the audience what you have there. This is cadmium sulfide, a semiconductor. When you see anything, you nudge me, right? If and when anything happens, tell me, all right? That's cadmium sulfide. This side is platinum. It's immersed into a liquid, an aqueous solution. If we watch carefully, something should happen. You look very carefully. I'm going to come with you, get closer, see whether anything happens there. Ah, I can see something. Can you see something?
Is it fluorescent?
No, it's not fluorescent. No, at least I can't see it to be fluorescent. Look at the top there. See what's happening there? Can you see what's happening inside? You see bubbles coming up? Can you? What do you see?
Bubbles.
Bubbles. Very good. I wonder if we can see the bubbles coming off there. Can you see them? There are bubbles just about being liberated from that cadmium sulfide. They're pretty visible now, there's no doubt. Thank you very much, Helen. Now, what you've just seen is part of an experiment that my colleague Dr. Tony Harriman does in the Davy Faraday Research Laboratories. Dr. Harriman is one of the country's foremost authorities on converting solar energy into chemical energy. What he has succeeded in doing there is to develop a photocatalyst. Remember what I said a catalyst was? A catalyst is a material that facilitates, that speeds up change. This semiconductor acts as a catalyst only when light is shining on it. And what we were doing there, as a matter of fact, those bubbles were hydrogen. So think what that means now. There's no shortage of water on Earth. If you get the right catalyst, if one has the right chemistry and physics to design the right photocatalyst, you can then liberate hydrogen, which you can then burn. What happens when you burn hydrogen? What happens? Do you know? What do you produce? What do you produce? Water, exactly. So that's a nice, convenient reaction, a very clean one. Doesn't produce any pollution. So that's the incentive. Now this takes us properly into the world of catalysts. Now I want to talk about platinum because platinum is an extraordinary important catalyst. In fact, Bryson is going to carry out an experiment. This is slightly hazardous, so he's going to carry it out. He's volunteered to. What I've got here is a black powder, which is a special Johnson-Matthey type catalyst, in which we have platinum and rhodium. And he's going to pour that catalyst onto that cotton. Now, before he does anything else, let me tell you, if everything works, what we ought to see. He's going to put just a drop of methyl alcohol. Methyl alcohol is plentifully available. And if that's a very good catalyst, that should burn, and burn quite briskly, even at room temperature. Off you go, Bryson. I'm going to stand back. We just have to wait a little, I suppose. My goodness me. You see, I'm glad that he did that. Now, that is catalysis operating at very low temperature. Platinum is a marvelous catalyst. I want to show you some film clips, one of some work I did in the University College of Bangor, North Wales, many, many years ago. Here are some platinum particles on a graphite crystal. And oxygen has just entered, and now this little particle is behaving like a badly behaved insect. You see, it's eating away at that leaf, so to speak. Here it is under an electron microscope. Look at this little creature behaving in a berserk fashion. Look at it, munching away at the graphite. It suddenly stops and then it jumps again. Look at it, and eats away that graphite. Now, that's catalysis. It's very important. Let me tell you an example of where platinum catalysis is extraordinarily important. In automobile exhausts, you generate incompletely burnt fuel. That is to say, you get carbon monoxide and some hydrocarbons. And that's what causes smog and all sorts of other nasty things. It's also hazardous because there's carbon monoxide there. Well, what the industrialists have developed is this little muffle. It's made of clay, incidentally. You can make this very easily. It's made in Royston, just outside Cambridge. There are thousands of little pores there running right along so that the exhaust can go right through. Now, if you take a material like that and coat it with minute particles of platinum and rhodium, and then put this in your car exhaust, when the carbon monoxide and nitric oxide and hydrocarbons go in, they'll come out at the other end as carbon dioxide and water and nitrogen, perfectly harmless. That's why 40% of the world's platinum at present is used not for platinum rings, but for platinum catalyst exhausts. Now, platinum has been used for a very, very long time. Let me tell you about this gentleman. This man looks anything but a scientist, but in fact, he was a phenomenally good scientist. He entered Oxford to study law. He became a successful lawyer. He ultimately ended up as a judge. In fact, Vanity Fair in 1884 had this cartoon, which is labeled somewhat ironically, galvanic electricity. Nothing less than electric and galvanic is that sight there, perhaps, but you would be wrong to think that. This man, Robert Grove, worked occasionally at the Royal Institution and also at the London Institution, a place that no longer exists. He made a very important discovery. It's a discovery which I want to take you back to the first lecture with. Let me say, first of all, what Grove wrote in a letter. Here is a photocopy of it. The letter that Grove wrote to Faraday on Saturday, October the 22nd, 1842. He describes what has now become known as the Grove cell. In each one of these receptacles, and here they are now, the facsimile of what Grove built. There's a tube which is inverted. In it, there's platinum, 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 and so forth. Platinum is immersed in the liquid, and it's also got, in that one, oxygen, in this one, hydrogen, oxygen, hydrogen, oxygen, hydrogen. And what Grove did was succeed in finding a way for getting hydrogen and oxygen to combine. Do you remember how it normally combines? In that devastating fashion, right? That's the way, if you have the right mixture of hydrogen and oxygen, it tends to explode, and it can be very dangerous. But Grove, being the ingenious man that he was, realized that he had tamed, he'd completely conquered that reaction, and he could pull out electricity from it. What Bryson is now going to do is, first of all, to electrolyze these 4 tubes. We're going to generate hydrogen and oxygen and hydrogen and oxygen, so that we have effectively 2 Grove cells. And when we've generated enough, and I will let Bryson decide when he has, we'll stop generating gas, we'll take off those crocodile clips, and then what we'll now do is test whether Grove was right. We'll measure the voltage, and lo and behold, it works. There you are, you see. When you put hydrogen and oxygen together, you can derive electricity from it. And we have our Christmas tree lit up, guess how? By light-emitting diodes. Thank you, Bryson. Well, now that is an example of platinum catalysis at its very best. Let me mention how highly significant that is. The Grove cell is now present in every manned space vehicle. Why? First of all, you can take up plenty of hydrogen and oxygen and you can generate the electricity. But there's another reason. You've got to provide water for the crew to drink. And the product of the reaction is water. So you kill 2 birds with the same stone. It's ironic that this marvelous gentleman, I'm very fond of this man, he's a brilliant scientist, he always took the very distant, purist approach to science. He's on record as having said that I cease to remain interested in a subject once it becomes useful. It's very ironic that the Grove cell is not only used in all space vehicles, at this very moment in downtown Tokyo, there is a massive power station which doesn't operate on the same principle as the Battersea power station or any other power station in Britain. It operates on the basis of a fuel cell. They have a platinum catalyst. They're burning hydrogen to oxygen. How do they do that? Well, Japan has very little source of power. It buys liquefied petroleum gas, which is propane and butane. It uses a catalyst to convert that to hydrogen. And then in downtown Tokyo, with an arrangement, much more modern and far bigger, of course, than this, you generate 400 kilowatts of electricity, enough to run a large hospital or a university or a community center. It may well be that in the 21st century, that's how we shall have scattered all over the world the clean, environmentally acceptable, compact, and highly efficient powerhouse based on catalysis and electrochemistry. But there's one other catalyst that I must mention to you, and with Andreas's help, I'm going to tell you a little bit about it. Andreas has placed up onto this graphic screen a catalyst that he and I and Professor Cheetham at Oxford are very, very interested in. This is greatly magnified. I should tell you that this little hole here is so small that if I put 1,000,000 of those holes next to one another, it would not be as large as the top of that pin. Certain molecules like methyl alcohol, methanol, can enter those channels very easily. And at this moment in New Zealand, where there's plenty of natural gas, unlike the situation in Japan, the natural gas is converted to methanol, and the methanol in this catalyst is converted to petrol. Petrol is made up, amongst other things, of benzene and xylene. There are other molecules, which incidentally are shown here, which cannot enter that hole. It cannot enter that aperture because they're too big. But let me go to this final slide that I want to show you. This is a catalyst. Both these catalysts, this one and that one, are called zeolite catalysts. This one was discovered in Sunbury-on-Thames about 3 years ago. It's called Theta 1. It has a beautiful channel, and in that channel, to scale, we've put a molecule of xylene, which is also a component of petrol. Originally, there were 2 molecules of butane or propane that could go in there, and in Alaska, at present, there's a superabundance of such molecules, so it's conceivable that on site in future, in many of the oil wells and gas outlets scattered all over the world, you'll be able to generate the petrol that you want. Well, my story is very nearly over. Before I cease to talk, however, I do want one volunteer, this young lady in blue. Come and stand here, Naomi. There's something going to happen to you. Mr. Smith is going to make you invisible. Go ahead. We've seen many practical uses to which crystals may be put. Here's how they're being used to save lives.